about the scattering mechanism. Okay, so we already talked about the mobility. Remember? Right? And last time I kind of mentioned what is the meaning of mobility. When your electron move due to the electric field, this is electron, and then you have an electric field, maybe the electric field come from here. It's everywhere, right? It does not just accelerate, it does not just keep accelerating to the light speed of light, right? Because I have a lot of atoms. I have a lot of things that making it to slow down. And this is called scattering. You can go from here. It can also go back, which makes sense, right? You run in the football field with many people. If you hit to a big guy, you are going to scatter back, okay? So then effectively, you have a velocity. This velocity is related to the electric field by mobility. Is that okay? So you keep scattering different direction, go back, and then lose energy, right? So what are the scattering mechanism? The first mechanism is the Coulomb scattering. So what does it mean? For example, when I have a lot of negative charge here, then I have an electron coming in. What will happen to the electron? Well, you're going to get scattered away, right? Right? And it might also scatter back if your electron actually go in this direction. Anyway, the message is that I have negative charge, the electron comes in, you don't have an easy life. You cannot just go straight. You are going to get diffracted to some places or scatter back. Make sense? That's called Coulomb scattering. Now, if in the world we only have this mechanism, then we will get a mobility which is related to the Coulomb scattering. We call it mu Coulomb. Now, let me ask you, if the electron is moving very fast compared to an electron moving slowly, which one get more scattering? Fast one get more? Think about this one. If this is one is moving very fast, now I think what you're thinking is that fast get more because you are trying to say slow electron get more Coulomb scattering. You say fast get more of slow. Why is that? Because it can get closer to but I did not say that they are the same distance from the other charge. Very good. Yeah. Slow electron, right? So slow electron. So get more scattering. Because you just imagine I really move very small, I keep feeling the field, right? Because I feel more the Coulomb force. So, if the temperature reduces, what happened to the speed of the electron? Is it slower and faster? Slower, yeah? Because this time, although we did not talk about that, the thermal energy is kT over Q, which is equal to the half mv squared. Because the so-called thermal energy is just the kinetic energy of the particle, right? So kT over Q, of course this is not exact, maybe 3 kT over Q, right? Here, I forgot, 3 kT over Q or whatever, or over 2, right? There should be a 2Q, right? Yeah. Higher temperature, electron move fast, particle move faster, right? Electron is just a gas, except it is charged and except that it is in the solid. It's just a gas, right? So lower temperature, slower electron, that means, now I want to ask you, higher or lower Coulomb mobility? Just KT? Oh, yeah. Thank you. That's why I don't welcome the physics student to come to the class. Okay, just kidding. Okay, then, now I try to trick you, right? So, lower temperature, do you have higher or lower mu Coulomb? Mu is the mobility. Lower. Why?
Because the electrons move slower, they get scattered more.
Very good. Because scatter more. Because you just now we keep discussing that lower temperature scatter more. I try to trick you. You may say, oh, you have lower mobility. Remember, lower mobility means you have more scattering. Okay? Don't mess up this, right? So it is lower, correct. So there is a problem for our, not problem, a characteristic, and very important actually for our cryogenic device. Okay? Then another thing is called surface roughness. This occurs because we have this. You have oxide, right? But if you zoom in, you will see the atom. It is not flat. And then your electron comes in. And you say you're conducting on the surface, right? So you just like I push you against the wall and ask you to run against the wall, but then the wall is very rough. Then you can imagine mobility will be reduced. So if I don't have other mechanism, then I call this mobility due to surface roughness scattering. Okay. Now you may argue many things as up to now no one argue, but may say in some scattering I don't lose the energy. Particular for this one, you may say that, hey, I go in, if I just like refraction, go out with the same angle, I don't lose energy. Yeah, there's two types of surface roughness scattering, right? One is diffuse, one is called spectacular, like mirror, is that spectacular? I forgot the name. Specular scattering, or mirror type, that you don't lose energy, it's elastic scattering. Another is diffusive, right? But we don't go into this detail, right? There's a lot of quantum mechanical treatment, which I don't know well either. But the point is you may lose energy. And then you lose your velocity, right? So this is the mu SR. Now, again, we are talking about when it is on the surface. So let me ask you, if I increase the gate voltage, or maybe I just put down this electric field. If I have a higher electric field, do I get more surface roughness scattering or less? Higher electric field means what? I'm pushed more against the wall, right? Then can you run faster or slower? So I'm running against the wall, and some of you keep pushing me against the wall. And it is very rough. Do I run faster or smaller? Slower. Slower, right? Because I get more scattering. So this is the problem. So when the Vg increase, electric field voltage increase, then of course it means the electric field, we call it oxide electric field, is going to increase. And eventually you have more surface roughness scattering, which means you have higher or smaller mobility. Smaller. Yeah? But we want to have a high Vg, right? Remember our device, we want to turn it on. Remember the transconductance? I don't have the slide now. If you go up IDVG curve, you have larger transconductance. Correct? So that is not good. The other thing is very trivial. Phonon scattering. What is phonon? Phonon is just the vibration of the lattice, right? And then you can do some quantum mechanical treatment, then it becomes a virtual particle or quasi-particle. It's not really a particle. You cannot do either equal to mc squared to get the energy from it. It doesn't have mass, but it's a particle because you can treat it as a particle in scattering or whatever when you quantize it. And you can have the second quantization to add a new phonon, remove a phonon. It's very easy to understand once you have the concept of phonon, right? But anyway, phonon scattering means the vibration of the lattice. And this is easy to understand, right? So if the temperature increase, then do I have more or less vibration from the lattice? More, right? Vibration increase, right? Or you can say the number of phonon or available mode will increase. Then as a result, you have more scattering, then your mobility due to phonon increase or decrease. Decrease. Yeah, if you forgot, you just remember it's lower, so it has to decrease. Right? Now, in reality, you have many types of scattering. Here are only the three major types. Okay? And what is the total mobility? Then we use this very useful engineering rule, Matheson's rule, which means the total mobility, the reciprocal of the mobility, total mobility, equals to 1 over the Coulomb mobility plus 1 over surface roughness plus 1 over Phonon, and you can keep adding if you find a new type of mobility. That include like remote phonon scattering, or surface phonon, 2D phonon scattering, or yeah, I forgot all these things. Yeah. And if you're interested in your project, you use TCAD Centaurus, just look at their manual. There are 100 of pages just to talk about the scattering mechanism. Yeah, because the transport is the most important thing, right, in any device simulation. Okay, so 3 things, right? We will revisit again later. Any questions? Okay, if no, then we go to new topics. We still need to understand even more. It's not easy, a lot of things, but we will repeat. We will repeat again in SOI, repeat again in FinFET, okay, but from different perspective. Now, first of all, I want you to, maybe you learned that already. If you have not, which is again fine, because this is not equivalent to 2 lecture or even 3 lecture if you take material science, the class related to this. But anyway, for any crystal, they are arranged periodically in the space, in the 3D space. And there are some direction. They have, of course, they have direction. You go in different direction, you will have different, you see different things, right? So you feel different things. As a result, you have different effective mass or you have different scattering mechanism because they are not isotropic. Isotropic is the same in every direction. So if you have an empty space, it's isotropic, right? I go up, down, left, and right. My property is the same. But not really, right? Think about, let me now, yeah. So let me stop here. So you have different orientation. This is a so-called Mueller index. This is 100 direction. This is 011 direction, and this is 111 direction. Right? It's just talking about the direction of the plane. Okay? And here I show the silicon native. So you can take a look at this book. This is free, right? By Berkeley Professor Cheng Ming Hu. Oh, this is slide. Actually, I don't know. I forgot where I got it. But he has some. He has a free book that is available also. Now, so what do I want to say here? I just want to say one thing if you have not learned this before. The first 2 things. One is that at different direction you see different things. Just a very fake feature. A crystal like this. Right. This is not a real crystal. Just from scattering point of view, going in this direction is very different from going in this direction. Do you agree? Because you see different environment. Okay, it's a very different environment. Maybe I did not draw it well. How about I do this? Maybe if I do this, I will make this very clear. Assume I have a crystal like this. Let me do it again, sorry. Going in this direction is very different from going in this direction. Now this is clear, right? Because the spacing is much wider in this direction, right? So just like this classroom, I ask you to run in this direction, all of you are going to be slow because you need to jump over this chair. But this direction will be fast. So I think you agree with me, in a crystal is anisotropic. This is the first concept, but this is related to the mobility. So I'm saying that you travel in different direction, you have different mobility. I hope you agree. Just take it for granted. Besides that, you also have different effective mass. Now, this is a little bit difficult to understand. So, electron has its mass. Electron mass is m0. This is free electron mass, right, in the space. Right, in the empty space. But when the electron travels in the crystal, it has a mass that is different from the free electron mass because of diffraction. In this case, you cannot treat it as a particle, you treat it as a wave, quantum mechanically, and then it's going to interact with the lattice. And as a result, you got the band diagram. And the curvature, this one, maybe I won't go into detail. This is the band diagram in 3D. This is the reciprocal space. Maybe let's just forget about it. I just want to say that if you are traveling in this direction, okay, you have an electron mass of 0.19 of the free electron mass. But if you are traveling in this direction, then you have the electron mass of 0.98 of the free electron mass, which is about 5 times heavier. Now, the electron mass determines the mobility, right? Because if I'm heavier, it's more difficult for me to run. So in silicon, you have so-called 6 valley. So we don't go into details, just trust me. Your electron can reside in each of these valleys. Now, this is not the real space. This is not x, y, z. This is the kx, ky, kc, which is the momentum space, right? But I don't want to go to detail because that would take another class just to talk about the reciprocal space. But only thing I want you to remember is that there are 6 valleys, and you can occupy any of these 6 valleys. Okay, but some of them may have different energy under different conditions. But however, the point is that when it is transporting, when you're transporting along this large curvature, it has a smaller effective mass. If it's transporting in the less curved direction, it's a heavier mass. So for example, if I'm transporting in the x direction, the electrons in these 2 valleys are going to be heavy because they are transporting in this small curvature direction. They are heavy, okay? But this one and this 4 are going to be light, okay? So I just want to introduce 2 things. If I transport in this direction, this is called longitudinal. And the longitudinal mass is 0.98 electron mass. Okay? And this guy, in this direction, it is called the transverse. And they are 0.19 electron mass. Okay, So let me say one more time. The only thing I need you to take home is that you agree the property of a crystal is anisotropic. This is the keyword of this one, right? If you forget everything, this is a keyword to interview. Anisotropic. Different direction is different. That's the thing. And not just the transport property is different. Even the effective mass is different. And again, I would say this is not difficult to understand in the sense that, think about me. I go in front, I can travel very fast. But if you want me to walk sideways, I am slow. I am anisotropic also in this sense. They ask me to go backward, even slower, right? But this is something you even don't have in nature, front and back, right? So you agree electron has different mass, okay? You have 6 value for silicon. You can reside in them, depends on which direction you're transporting. You get different mass. It can be as much as 5 times different. And their property is anisotropic, okay? Any questions? Yeah.
Curious, is it some attraction or repulsion within the lattice?
Yeah, it is like diffraction. You're right. So the electron interact with the lattice. But again, this is like you solve the Schrodinger equation, come up with everything, and then effectively you try to find the so-called group velocity of the electron. And then you find out that it depends on the curvature of the EK diagram. But yes, the fundamental thing is because of this periodic structure, then you get diffraction and refraction, and that's why you can have this electron mass. Yeah.
So the lower the effective mass,
Yeah.
so
The lower the effective mass, the faster you can transport. But is it better? That was I can tell you something, right? So people search for low effective mass material. Indeed, they can find a lot. But the problem is the density of states is very small. So as a result, finally, we want to have a lot of electron for transport. So that is a trade-off. So good, yeah. Okay, so let me go a little bit faster. Now, I show you the mobility. So here I want to show you some of the work we did. First of all, you do need to understand what it's talking about here, right? You don't need to remember this curve. Undoped bulk electron mobility. What is the meaning of undoped? Low impurity in this case, right? Of course there is, but very low. Undoped, so what is the mu Coulomb? Very small. No, you trick me. Small what? Small in terms of what? No defect, no scattering. Very small scattering. But it means the Coulomb mobility is infinity. Right? When it is bulk, what does it mean? It means is I'm not transporting at the surface. It's just a crystal. So I don't have surface roughness scattering. So this mobility is purely just the phonon scattering. Yeah. So here are some experimental data, and then we derive some equation to fit them. You can see, first of all, when you go to low temperature, so here a different temperature. This is 300 Kelvin, and this is 8 Kelvin. This is velocity, this is electric field, right? So what we're talking about is V equal to mu times E. So when you go to low temperature, this mu, which is mu phonon, is going to increase, right? Correct? So as a result, you do see that in general, all the curve goes up. That's the first message. Now, second message is about the king here. You get something called negative differential mobility. How to say this? Let me write here. Here, we call it negative differential Should be differential with mobility, yeah. Right? You see that the mobility actually gets smaller when you go to a higher electric field. So I will explain later that this is only occurs at low temperature and certain direction. This is 111 direction. This is 100 direction, okay? Which is here. If you transport perpendicular to this triangle direction, then you have this curve. If you transport in the 10C direction perpendicular in the x direction, then you get this curve. Very different. Okay? We have control. We just apply the electric field in that direction. Then you will transport along that direction. Yeah. Now, this is for hole, right? We mostly talk about electron. Hole also have this negative differential mobility. Okay? So in our paper, we actually derive this equation. I mean, we fit this equation. We did not derive to all the data. So that is the main point of the paper we have. But now, is that okay? Again, at higher temperature, this is 430 Kelvin, and this is 6 Kelvin. Okay, so you see a 10 orders increase in mobility when you go to 430 Kelvin to 6 Kelvin, which looks great. I have a 10x higher mobility, right? Now you just said you want to have a higher mobility, right? If everything else is the same. So let me explain a little bit why we have the negative differential mobility for electron at low temperature. Again, what I'm talking about, this is hole, it has it. But what I'm talking about is this. Velocity increase when you increase the electric field, but then it becomes smaller when you have a larger electric field. So why is that? So this is like this. I already told you this is longitudinal. If I transport in this direction, I go to x direction, longitudinal, right? And these valley are the transverse because they all have heavy electron mass. If you try to see the electron going in this direction, the curvature is much smaller. So it's light electron mass. Sorry, I say the wrong thing. This is with 0.19. This is 0.98 and 0. Okay, so what happened, right? So first, at very low temperature, okay, and low E field. At very low temperature and low E field, right? So electron is just resides in their valley. Okay, so if you were here, then you stay here. If you're here, you stay here. You still have the same mass. Okay, so when I increase the electric field, I just increase the velocity. Okay, so there's nothing special. So when I increase the E field, I will just increase the velocity, right? So that's why it goes up. Now, what if it is at low temperature, but medium electric field? This is where we get the negative differential electric field. Now, those electrons, now I call it the light electron, they will gain energy more than the heavy electron. Okay? And they will scatter to the longitudinal valley. Or let me just call it heavy valley. Okay, so what I'm saying is that, I look at the red lines. This electron is going to scatter to here. Okay, so as a result, you have more heavy electron. And that's why the mass increase and mobility reduce. That's why you get this negative differential mobility. Okay? Then why you don't have this problem at high electric field or at high temperature? Because scattering also occurs from heavy to light valley. Okay, so you have some more equilibrium. Because when you are at high temperature, they can get phonon easily. This will go back. So you have some light electron become heavy electron, also heavy electron become light electron. So overall, the population doesn't change. So as a result, you have the same mobility. Okay, so that's why your velocity does not change. Probably confusing, right? It's not easy to understand. But try to understand again. I'm not going to test this in the exam. But when you try to understand, you will realize that you understand some very important concept, including now you realize that I have 6 valley. I have 6 valley. Each of them behave differently when you transport in a certain direction. Electron can be considered as light and heavy. Okay? And they can scatter from each to another. But however, at low temperature and at low field, you cannot scatter. Okay? And that's why at low temperature and medium field, you only scatter those light electrons to be heavy electron. As a result, your velocity reduces. That's why you get this negative differential mobility.
So, low temperature, medium field. I thought we established that the slower the electrons move, the more likely they are to scatter. So then if they're going faster, why would they scatter too?
Not slower, but light electron. I mean, this scattering is due to the electric field, not due to Coulomb force. You're just pulling me. I keep gaining energy. I'm energetic enough to go to another valley. Yeah, it's not due to Coulomb scattering. Yeah. Okay, then here again is just to understand what it means. What is the meaning of dope? It means you have impurity. Yeah, so your mu Coulomb is what? Finite, right? It's no longer infinite, right? So smaller than infinity. But again, it is bulk. So what is your mu SR? Do you have any surface roughness? No, right? So this is still infinity. Right? So here is showing some very old experimental data, and we try to fit it with a model. And we think that some of the data point might be actually inaccurate, even we fit it well or we don't fit it well. But here shows that the top is like doping is 3.1 E14 per cm cube. The bottom is 1.5 E19 per cm cube. Here clearly shows that the mobility reduced by at least 2 orders of magnitude, 10,000 to 100. Oh, no, 3 orders of magnitude. How many? 2 orders of magnitude, right? Is this 10,000? Yeah, 10,000 to 100, right? Because when you reduce the Coulomb scattering. Again, of course, when I reduce the temperature, the mobility goes up, right? But then it goes down again, right? Although we say there might be some error, this is old experiment. But why it will go down when you go to low temperature? Can someone explain to me? For example, let's look at this gray one, right? So when I reduce the temperature, the mobility keep increasing. Why? Why when I reduce temperature, the mobility increases? No, I'm asking about increasing here for this part. Because you have less photon scattering. And then, why it decrease again? Coulomb scattering. Because now Coulomb scattering become important because it's low temperature. Here, Coulomb scattering is not important because I have a high thermal energy, travel very fast, very small Coulomb scattering. Okay? So Coulomb scattering, but even for some very low doping, we still have problem because you still have impurities, which is not trivial. Okay. And that brings us to a very important curve called Takagi's Takagi jet universal mobility. It turns out that no matter how thick your oxide is, what doping you have, and across many technology nodes since 1970, 80s up to early 2000, if you try to plot the effective oxide field against the mobility under the transistor, they all follow the same trend. Okay? Different doping and different things. Except here, right? Why? This is what we already said. Our total mobility equals to 1 over Coulomb mobility, right? Which is this part, plus 1 over Phonon, which is the middle part, plus 1 over surface roughness, which is the last part. What does it mean? Surface roughness is only important when I have a large electric field. You don't push me against the wall, I don't feel it. If you push me so much, then it dominates because this becomes small, then this term becomes large. 1 over small is large. So this part is surface roughness. Okay? Now when you don't have high electric field, then you don't have much degradation due to surface roughness, but then you start to feel the effect of phonon. When you are low temperature, then it goes up. Like this 77 Kelvin, the whole thing goes up. But if you have very high temperature, very high electric field, 77 Kelvin and 300 Kelvin merge because they all both dominated by the surface roughness. If you have very low electric field, then the Coulomb scattering will dominate because at this point surface roughness is not important, but depends on the temperature. If you have a very low temperature, then you will start seeing the Coulomb scattering. For example, 77 Kelvin, I have less photon scattering, so I see this going down, right? Or if I have a very high doping, it will go down earlier. Okay, so remember these three have some interaction with each other. So free scattering, Coulomb, phonon, and surface roughness. And that is all we are going to play with later for SOI, FinFET. We just look at these three types and we determine what it will happen at lower temperature. This is an example I just want to show you, and this is from SJSU, our paper. We did the measurement here. It's just like what people did, right? So this is from another paper. You see at 300 Kelvin, if you just reduce the effective field, but of course here it puts the charge, but this charge, you can just think of it as proportional, right? Do you remember the charge is proportional to Cox times Vg minus Vt, yeah? Which is proportional to the electric field, okay? Effective electric field, like what I showed you earlier. So here is electric field, here is the charge. For 300 Kelvin, you do see that when I reduce the electric field or charge, I do get higher mobility, right? But, and that is what we see here for low temp, 300 Kelvin. But when you go to 4 Kelvin, I don't have more phonon scattering, so I have very high mobility. This is mobility. I have very high mobility. But then I drop down very fast here because the Coulomb scattering dominates a lot. It just pull down everything. Okay. And there's something called screening I did not discuss, but let's just ignore that for now. That's the reason why you see Coulomb scattering at low electric field. Maybe I need to say that. Here, screening means that you have a mobile electron, it screens away the electric field, so you don't feel the Coulomb scattering. Okay. Now then, this let me see. Even cannot finish this. I want to finish this transconductance. This just something at low temperature. Look at this book. What happens there is that sometimes you will get a spike on the mobility, and the reason is because you have a different subband in the layer. So what do I mean here? If you look at the inversion, remember this inversion? This is the oxide, right? In inversion, you actually form a triangular shape. You actually have quantum confinement to form the first and second and third subband. You can only reside there. So from quantum mechanics, you take it for granted when you have very narrow well, you can only have discrete state. So that is the same for a transistor. But you don't feel that at room temperature because you have large thermal energy. But at cryogenic temperature, you will start seeing this effect. That is one thing. And people try to model the mobility with this model. I don't need you to learn. Just treat this as a cheat sheet, or in the future, if you need, you can refer. You know that you can find out the relationship of mobility as a function of temperature. Okay. And similarly, this is the transconductance. We have learned transconductance. What is transconductance? Gm equals to partial ID, partial Vg, right? And here, you will see the transconductance will increase when you go to lower temperature. But interesting thing is that you will get into negative transconductance. You see that the current decrease when I increase the gate voltage. So this is very interesting. This is our experiment, and this is other people's experiment. That is just because when you go to the high electric field, and at low temperature, you don't have phonon. So the scattering becomes so much, the surface roughness increases so much that you actually get lower current, right? So mu s are reduced at high Vg, and then you have lower current, okay? And then a model for velocity saturation. Okay, I think I need to stop now, but I just want you to understand that the velocity, saturation velocity is also changed as a function of temperature. Okay, we will refer to that in the future again. Okay, any questions? Yeah, if no, let's stop here.